Welcome back, Focus Learners. I am absolutely thrilled to have you here today. I'm putting on my Master Tutor hat right now because we are taking a deep, detailed look inside the very brain of your computer. We're breaking down computer architecture. So if you're gearing up for your exams, you are in the exact right place. We're going to decode the CPU, figure out exactly how it talks to memory, and most importantly, I'll be dropping some high-value exam tips straight from the syllabus to help you lock in those top marks. Okay, let's dive into the game plan. Today we're covering the von Neumann architecture, then zooming into CPU registers and buses. After that, we'll watch the Fetch-Decode-Execute cycle in real time, see how we can boost CPU performance, and wrap it all up with instructions and embedded systems. Let's get to it. All right, Section 1, the von Neumann architecture. To really get modern computing, we kind of have to travel back in time first. Now, you might be wondering why this is such a big deal. Well, before the mid-1940s, early computers were incredibly tedious. They basically couldn't operate without constant human intervention. I mean, data had to be physically fed into the machines while they were running. But then, John von Neumann developed the concept of the stored program computer, and it literally changed everything. By storing both the data and the programs in the exact same memory space and letting the CPU access that memory directly, wow. Suddenly, programs could execute automatically in sequential order. It was a total game changer, and it's the very foundation of the devices we're all using right now. Moving on to Section 2, let's actually crack open the CPU and look at the internal anatomy, specifically the registers and system buses. So the absolutely crucial thing to know here is that the CPU relies on what we call registers. Think of these as fundamental, high-speed, temporary storage pockets right there inside the processor. It's the CPU's short-term memory. For your exam, you need to know these 5 special-purpose registers cold. The program counter, or PC, is basically a bookmark. It stores the address of the next instruction. Then there's the memory address register, the MAR, which holds the exact memory address we're reading from or writing to. The MDR holds the actual data we just pulled. The current instruction register, the CIR, safely holds the instruction while it's being decoded. And lastly, the accumulator. This guy temporarily stores the results of whatever math or logic the CPU just crunched. But here's the thing. Registers are pretty much useless if they can't talk to the rest of the system. Enter system buses. These are parallel pathways, essentially microscopic wires connecting the CPU to memory and I/O devices. Think of it as the computer's central nervous system. You've got 3 types to memorize. The address bus, which carries the location data, the data bus, which carries the actual instructions and data back and forth, and the control bus, which carries timing signals like the system clock to make sure everyone's playing to the same beat. Now pay close attention to the directionality here because it's vital. Okay, listen up, because here is a massive Master Tutor tip for you. Examiners will literally hand you a free mark just for stating clearly that the address bus is unidirectional. It travels one way and one way only, from the CPU to the memory. Why? Well, imagine if memory addresses accidentally flowed back into the processor. It would be total chaos. The system would crash. Conversely, the data bus has to be bidirectional, so data can easily flow both to and from the CPU. Make sure you memorize that specific distinction. All right, Section 3. We've got the anatomy, we've got the nervous system. Now let's watch this machine actually think. Let's look at the Fetch-Decode-Execute cycle. Let's break down this highly rigid step-by-step logic. Every single action your computer takes starts with the fetch stage. Step 1, the program counter sends its address to the memar using our famous unidirectional address bus. Step 2, the memory gets a read signal and the actual instruction sitting at that specific address travels back to the CPU's MDR using the bidirectional data bus. Step 3, the data is copied right into the current instruction register, so it's prepped and ready for translation. And step 4, this is key, the program counter is incremented by 1. That way, it's already pointing at the next instruction in line while the CPU handles the current one. So, once that instruction is safely sitting in the CIR, we move to decode and execute. In the decode phase, the CPU's control unit steps in to interpret the instruction. It's essentially translating the binary so the hardware knows what physical action is actually required. Then, during the execute phase, the CPU gets to work. It sends out control signals along the control bus to various hardware components, maybe firing up the ALU to crunch some numbers, or instantly writing new data back into memory. And after that, the whole cycle starts over again. So if your computer relies on executing billions of these little cycles, it brings up a really obvious practical question. If this rigid step-by-step process is fundamentally how computers think, how do we physically make them think faster? That brings us to Section 4, boosting CPU performance. Let's look at the hardware upgrades that really move the needle. Your overall CPU performance essentially comes down to a few major hardware factors. You can widen the system buses. Think of this like adding lanes to a highway, so a whole lot more bits can travel at the exact same time. You can add cache memory, which is super fast SRAM located right inside the CPU. It holds frequently used data, which saves the CPU from having to hike all the way over to the main RAM every time. You can also use multi-core CPUs, like a dual or quad core. That essentially gives you multiple internal brains to process things simultaneously. Though a quick caveat, doubling your cores doesn't magically double your speed, since the CPU still has to coordinate communication between those cores. And finally, you can increase the system clock speed. Let's put that clock speed into perspective. A typical modern processor might run at around 3.5 gigahertz. Because the internal clock synchronizes all the operations, that means your CPU is successfully performing 3.5 billion Fetch-Decode-Execute cycles every single second. That's enough to make your head spin. It's staggering. But does that mean you can just crank the clock speed up forever to get a faster PC?
The answer is a hard no, and this is another one you'll want to remember for the exam. Going into your BIOS to force the clock to run faster than the factory recommends is a process called overclocking. If you push it past its actual design limits, operations start getting unsynchronized. Basically, an instruction literally won't have enough time to finish executing before the next one is shoved down the pipeline. The result? You're looking at serious overheating, massive system instability, and frequent crashing. Faster is definitely not always better if the hardware can't keep the beat.
And finally, Section 5. Let's take a look at the actual language the CPU reads and where we find these processors out in the wild. So every single piece of machine code your CPU decodes is made up of two parts, the opcode and the operand. It's actually pretty straightforward. The opcode is the action. It tells the CPU what to do, like add a number or jump to a new address. The operand is the target. It's the actual data that needs to be acted upon or the specific memory register where that data lives. When you put them together, they form a complete instruction. All the possible opcodes a specific CPU can understand make up its instruction set. Right, time for my final master tutor tip to save your grades. Please, do not confuse instruction sets with high-level programming code like Python or Java. Instruction sets are the absolute base-level, low-level binary commands that the CPU hardware physically understands. When you write standard programming code, it has to be completely translated or compiled all the way down into this very specific instruction set before the CPU can actually do a single thing with it. Now, keep in mind, not every CPU is sitting inside a glowing gaming PC or a sleek laptop. Millions of them belong to what we call embedded systems. If you're taking notes, memorize this exact phrasing for the exam. An embedded system is a combination of hardware and software designed to carry out a specific, dedicated set of functions. Unlike your laptop, which is juggling a web browser, a video game, and a spreadsheet all at once, an embedded system is built to do just one thing, flawlessly, repeatedly. You interact with these all day long. The microprocessor inside your washing machine, it only knows how to manage water levels, spin cycles, and temperatures. The engine management system in your car, it just monitors sensors and adjusts fuel injection. Your microwave just times radiation and spins a glass plate. These are all embedded systems. They're using the exact same fetch, decode, execute cycles and registers we just spent the whole session breaking down, but they're locked into a highly specific instruction set for a single dedicated purpose. Which leaves us with a pretty wild thought to chew on. We've seen just how rigid and specific this hardware architecture really is, right down to the system buses and the cycles. But as artificial intelligence continues to merge with physical hardware, what happens if these everyday embedded systems gain instruction sets that can adapt and reprogram themselves on the fly based on their environment? What is the brain of the computer going to look like tomorrow? Anyway, thank you so much for joining me for this explainer. Keep studying those registers, and I'll see you in the next one.